There we go. All right. So in our solutions chapter, we actually get to explore what you've been doing. Well, you were doing before we left campus in a lab, and you were working with solutions. So we would put out bottles and we would say, hey, this is 3 molar acid, this is 6 molar acid, and now we're exploring what's actually in that solution. So inside of a solution, we have a solvent and a solute. And obviously the solute's much larger here than would be in real life. These look like little tiny ping pong balls in there. But the idea is the solute are particles that are essentially dissolved into our solvent. So the solvent will always be what you have more of, the solute what you have less of. So in general chemistry, your solvent is almost always water. If it ever is not water, we always identify it on the bottle. We will say this is dissolved in hexane, or this is dissolved in dichloromethane, or whatever it's dissolved into. But most of the time in general chemistry, your solvent will be water. So if we were just to hand you a solution, say, hey, this is 3 molar HCl, you would be very safe in assuming that that solvent is water. Now, when you move on to organic chemistry, that changes. Your solvent is rarely water, and they will always identify your solvent. But again, in general chemistry, we identify the solute and assume the solvent to be water. So the definitions here, which I do want you to know, is the solvent is always the more abundant substance. So whatever you have more of, that's your solvent. The solute is always what you have less of. And you can have a system with more than 2 things. Let's say you have 3 things. Whatever is the most plentiful, which you've got the most of, that's your solvent. And whatever you have less of, that becomes your solute. Now the solution is a homogeneous mixture of 2 or more substances. And we learned about homogeneous way back when, before you knew how much fun it would be to do an online class. Does anybody remember what homogeneous means? Yes, so I'm seeing the same, and it means the same throughout, that it is mixed perfectly. Excellent. It is mixed the same, yes. So one of the things that our lab techs do is they make homogeneous solutions for us. So if they put out a bottle and they say it's 3 molar, it needs to be 3 molar throughout the whole thing. Because imagine a situation where they put out a bottle, and it's more like when you get I want to say a mocha from Starbucks, and it's more chocolatey at the bottom and less on the top. So if something like that were to happen, then the first person who gets some of that acid has it less concentrated, and the person who gets it from the bottom of the bottle has it more concentrated, and that would mess up our experiments. We have to have it mixed perfectly. And if you're wondering, yes, our lab tech is a perfect mixer, but also our solutions tend to mix perfectly. That's how we make our solutions. We actually put a magnetic stir bar into the beaker or the Erlenmeyer flask, and we set it on a magnetic stir. Most of our hot plates have a second knob on there, which I think we got a chance to use our hot plates at least once. If you saw the second knob, that's for the magnetic stirrer to make it a homogeneous solution. So that's a really important part of the lab tech's job, to get us a homogeneous solution. And again, it could be 2 or more substances. And something that you already knew, you just didn't know the definition of, and that is an aqueous solution is something where things are dissolved into water. So in other words, if water is the solvent, we then call it an aqueous solution. So any questions on anything so far? So I mentioned you can have more than 2 things in a solution. We also have different types of solutions. So for example, our air is a solution of gas. So within the local area, so I know that the air that I'm breathing might be slightly different than the air that you're breathing, but within the room that I am in, the air should be mixed homogeneously, and there's lots of different gases. So inside the air that we breathe, we have argon, we have nitrogen, we have carbon dioxide, we have O2, we have all sorts of things, and they should be mixed perfectly, and that makes a solution. The solvent would be the gas that is in greatest quantity of all those gases. Next up, gases and liquids can make a solution together, and every one of your carbonated drinks has that. The carbonation comes from CO2 gas that is mixed in there, and the liquid, usually that is coming from water, so those are usually water-based or aqueous solutions. You can also have two liquids, so drinking alcohol is a mixture of water as the solvent and ethanol, which is what I like to think of as the business end of the alcohol. That is the alcohol part of your drink. But when you mix those two together, that is a liquid-liquid solution. You can also have a solid liquid solution. So you can mix salt and water, salt being your solid. If water is in greater quantity, and then it is an aqueous solution, and the water becomes your solvent. Next up, you can have a solid-solid solution, and this is kind of a weird thing. If you were to actually mix two solids in their solid form, and you just kind of mix them up in a container, it'd be really, really hard to get them homogeneous. So what we actually do is we melt them down, mix them in their liquid form, and then let them solidify. And this we see in brass, but we also see it in steel. So when you think of the beams that are holding buildings together, those are solutions, technically, even though they are solids, because they had to be mixed perfectly in there. And if you're wondering, there is an entire science, I believe it's normally referred to as material science, and that is dedicated to steel, brass, the mixture of those solids. When I was in graduate school, because my research group did geochemistry research, I had to take a semester of that. And one of the students that I was in class with, she ended up, after graduation, working for U.S. Steel. So the idea is they have to have that steel mixed perfectly. Because if there's an imperfection in that steel, and that is part of a skyscraper, that during an earthquake, that could cause a crack. That could cause the building to come down. So it is really important that they get that perfect homogeneous mixture when the metals are in their liquid phase, and that they solidify them properly so that they keep the structure of a building, especially during an earthquake, and especially if it is a high-rise skyscraper type building. So any questions on anything here? I know it kind of changes your idea of what you think of as a solution. So normally we think of our solutions as only liquid-based or water-based, but now every time you take a deep breath, you're like, I'm breathing in the solution. All right, so next up is the second law of thermodynamics, and you're going to learn a lot more about this next semester. Tessa, I so appreciate you laughing, because I know my jokes are sometimes really bad, and I'm like, oh, I should have told that. They're probably thinking I'm so stupid, and then you laugh, and I really appreciate that. All right, so second law of thermodynamics. Again, you're going to learn a lot more about this next semester, but here we're just going to treat it briefly. And the idea is that the universe tends towards disorder. So entropy or chaos is always increasing in the universe. So over here, we have a glass of water and some food coloring. So if you put a drop of food coloring in, you know that it does not stay as just a little drop right up here. It starts mixing, and it starts mixing spontaneously. And even if you do not stir it, it will keep mixing until it is uniform. So the idea of entropy and the second law of thermodynamics is that things get mixed up naturally. That is where the universe is always spinning towards more chaos, more entropy. So one way I like to think about this is you come home from a hard day of chemistry class, you kick off your shoes, you put your jacket one place, you put your bag another place, and if you didn't take the extra effort to clean up, your place would just get messier and messier and messier, and that is the natural order of things. It really is that if you don't put in some effort, everything starts getting mixed up. Those of us with long hair know how bad our hair looks in the morning, and that is because of entropy. Nobody wakes up, unless you have really short, perfect hair, with hair perfectly groomed in the morning. You have to put in some effort to straighten it out, because what the universe says is, hey, it's nighttime, I get to mess up their hair. The universe is always trending towards things becoming more disordered. That is actually favorable from a chemistry point of view. The more chaos, the more things are mixed up, the more favorable it is for the chemical reaction. So in other words, mixing increases our entropy, and it is favorable to have that increase in entropy. However, sometimes we're going to see intermolecular forces get in the way. So if I go, yes, I see, doesn't the chaos result in a desire for equilibrium? Things are always spinning towards equilibrium, but the universe would prefer to set up an equilibrium state where there is more chaos versus less. So if we go back to this example here, we see that our food coloring just spontaneously starts to disorder. And back to Andrew's comment, once it is disordered, once it has perfectly mixed, so imagine it is perfectly mixed in here, that is the new equilibrium that it will set up. So essentially it's going to get as mixed up as it can, and that is its new equilibrium. That is its desire to have the most chaotic equilibrium possible. Universal effort. Let's see. So the universal effort that holds it all together. So what do you mean by the universal effort? So Clinton, I'm looking at your question, and what is the universal effort that holds it together? What do you mean by universal effort? Do you mean like why don't things just go spinning out of control? Yeah, no worries. So our theory is that things are slowly spinning. Oh, no worries, no worries. Things are slowly getting more and more chaotic. That's our theory behind the Big Bang. In terms of an atom, we say that there's a nuclear binding energy, and that's what keeps things together and keeps things from getting too chaotic. But in terms of the universe in general, the theory is that if we waited enough time, things would eventually just keep spreading out, and they would just continually get more chaotic. But there's also sort of a balance. So one of the arguments against this idea that everything's tending towards disorder is they say, well, what about human beings and animals? We're very orderly beings, right? We have organ systems, we have muscle systems, we have all this stuff going on that's very orderly. So doesn't that go against the second law of thermodynamics? But the theory is that humans, while we're very orderly in our bodies, what we do to the universe, we consume food, we put it out as energy, that we actually cause more disorder in the universe than the orderliness of our own bodies. So there are those two factors, but our law of thermodynamics say that whenever you have, say, sort of an orderly being, like a human being, we always cause more chaos than the order that we have in our being. And I don't know if that answers your question completely, other than I would just say that it's neural tissue is... good question. So that would be a good question for a physiologist. I don't know if I could comment on the neural tissue. But I do believe that the neural tissue is created as the fetus is developing. And if I remember correctly from physiology, this was many years ago, that you were right that it does not regenerate. So created as the human is created in the womb, and then how it is kept, I would have to look into the structures for how it's kept. Yeah. But that would actually be an example of that second law of thermodynamics, that the neural tissue is degrading as many of our tissues are degrading, creating more chaos. Yeah, sorry I can't give you a better answer on that. But I find the second law of thermodynamics to be really fascinating, especially when you just think of the world in general. If you were ever a teenager who had a messy bedroom, you know that just it happened. It's not like you said, hey, I'm going to put a shoe over here and a jacket over there. If you've ever been around a large group of children, you know their natural tendency is just to yell and scream and go everywhere. So that is all examples of the second law of thermodynamics. Okay, So moving on though, sometimes our intermolecular forces get in the way of entropy. So one of the arguments against this second law of thermodynamics is people look at this and they say, well, yeah, food coloring will spread out, but what about oil and water? Oil and water doesn't mix. And the problem is their intermolecular forces. So we have a saying that is like dissolves like. So for this entropy to work, for things to get mixed up and chaotic, we have to have similar intermolecular forces. And what we see with oil and water is that water is polar while oil is nonpolar. So if you have different intermolecular forces, you can shake these up, you can put this on a magnetic stir, you can try all you want, and you could, for a short time, get them to mix, but eventually they will settle out. And here it's because oil and water don't mix, but the real reason is they have different intermolecular forces. And we're going to talk in a minute about how that affects them and why they don't mix because of those intermolecular forces. But any questions here? Oh, yes. This one right here? Yes, okay. So let's pause on this slide right here so everybody gets a chance to copy that down. But any questions on anything so far? If anybody, okay, excellent. If anybody ever complains that your room or your house is messy, you can just say, hey, I'm following the second law of thermodynamics. The universe wants it to be this way. All right, so just a little fun cartoon. So here's water saying, I'm sorry, we just can't be together. And here is our fat molecule saying, is it because I'm fat? And water says, well, because water is polar and fat is nonpolar. So water and fat do not mix because of difference in intermolecular forces. Just for the fun of it, water is polar, and what is its strongest intermolecular force? Yes, hydrogen bonding. And if fat is nonpolar, what is the only intermolecular force that it has to its name? Yes, London dispersion forces. So those London dispersion forces, those were our temporary dipoles. So the idea is water is extremely attracted to other water molecules. Ah, good question. So why it's called London? So it's actually a common mistake that it was discovered in London. There was actually a person who worked on it who was responsible for the discovery whose last name was London. So a good question, Jervin. All right. So water has hydrogen bonding. It is extremely attracted to other waters because of those electrostatic attractions, because of the positives and negatives. So when a fat gets in the way, it's very sad, but it really does kind of push that fat out of the way because it is trying to find other molecules that can hydrogen bond with it. So poor fat gets shoved out of the way. So here is another way of saying this, and it says this. If the solute-solute interactions and the solvent-solvent interactions are more favorable than the solvent-solute interactions, then they will not mix. And yes, this is exactly why oil and water won't mix. So here, when we talk about solute-solute, what I'm going to say is the solute is more attracted to other solute particles. And here for the solvent-solvent interactions, I'm going to say the solvent is more attracted to solvent particles. They will not mix. So this is what's happening if you want to think of oil and water or fat and water. The water is the big problem. It has that hydrogen bonding and it is very attracted to its fellow water molecules. It has no interest in something that only has London dispersion forces. I don't know why I did that. I don't know if the camera caught it, but I kind of went like that. It has no interest in those oil particles. So when it is more attracted to its fellow molecules. Yes, lava lamps, exactly. It's the same thing happening in the lava lamps. So solvent, more attracted to itself. Solute, more attracted to itself. They have no interest in having a solute-solvent interaction. So this right here would be our oil and water. So oil would prefer to be with oil. Water would prefer to be with water. You can mix them up for a short time by shaking them, by having a lava lamp where they're being forced to mix. But when you turn the lava lamp off or when you put that oil and water mixture down, they do separate back out because they would prefer to be with their own kind of intermolecular force. You can actually make lava lamps at home. Back when I used to teach high school, we used to make little lava lamps. They didn't go automatically. You had to shake them, but they were lots of fun. So if you're looking for a fun activity for your kids, they are a little messy, especially if you put glitter in them. But some oil, some water, some food coloring, glitter, kids love it. And you can teach them about entropy. For making the lava lamp, no, I mean, I always just used, I think, just standard vegetable oil. All right, to other questions. Yes, so let's talk about water and salt. Oops. Oops, accidentally deleted that page. So Jervin has a great question. So if we have something like water, and I'm going to put my double negatives and my double positives because this can hydrogen bond. And we have salt, NaCl. Now what we see is we have what we sometimes call an ion-dipole interaction because here the negative is very attracted to the positive. This negative is actually more attracted to that positive than it is to another molecule because sodium has a full positive charge. So here, these are very attracted to each other. If we only had two waters together, shrink this down a bit. Here in this lower picture, we do have a hydrogen bond, which we normally think of as strong, but there is something stronger, and that is a bond between the water and the sodium. And the reason it's stronger is because you have a full charge here. So water is actually more inclined to bond or to interact with sodium than it is with another water molecule. So in terms of what we're talking about with the solvent and the solute interactions, here the solute-solvent interaction is more favorable than the solvent-solvent interaction. Does that sort of answer the question? Okay, good. Any other questions so far?
What about the whole what is salt considered? That's the solute, right?
In this case, yes, I was thinking of our salt as our solute, yes.
So the interaction between salt and water is more favorable. I'm sorry, excuse me, more favorable than the interaction between two salt nodules.
Oh, I see what you're saying. So this is our solvent, and this is our solute. So in terms of water, the solvent solute is more favorable than a solvent solvent interaction. But I think what you're then saying was, what about the NaCl?
Yeah, does the solute interaction have to be less favorable than the solvent solute reaction?
Right. So now maybe you're thinking of these two have full charges, so they should be more attracted to each other than they are to the water, right?
Yeah.
So here we have the ionic bond, and it is true they are more attracted to each other than they are to the water. But what ends up happening, and actually let me flash forward. What ends up happening is the water surrounds each of these ions, because the water is extremely interested in these ions, and it surrounds them not just in a circle like what's on the screen right now, but it's actually in a full ball. And the way I kind of conceptualize it, if you ever saw that Harry Potter movie where he really wants to fight, but Dumbledore put him in a ball of water and he couldn't get out, that's actually what happens here. So we say that they are solvated, they are surrounded by solvent, and they actually are isolated from each other to the extent that they can't find each other anymore. So water essentially steals them away from each other. So you are absolutely right that the attraction between a full negative and a full positive, try one more time, there we go. Full negative and a full positive is greater than the attraction between, in this case, a negative and a partial positive. But chloride doesn't have a choice because it is very much ganged up on by an entire ball of water, and in that sense they cannot find each other. So the attraction, the positive negative attraction between the chloride and the sodium, it's not there because they don't see each other, because these balls of water effectively isolate each other. However, what we're also going to learn in this chapter is in the real world, every once in a while, a water molecule moves just slightly, and when it does, they can sense each other's charge, and boom, they get back together. Because you were right, they would prefer to be together. And so if the water, which is kind of its jailer, moves just slightly, they get back together in solution. So you're absolutely right. The sodium and chloride, their attraction to each other is much stronger because they have full charges, but the water prevents them from getting together whenever it can. It solvates them, separates them out, because for water, it would prefer to be with the sodium chloride than another water. So did that sort of answer your question?
Yeah.
Okay. You're welcome. Good stuff to look forward to for next class. All right. So other questions on anything so far? But Jervin is right that in terms of the charges, the stronger the charge, the more it is interested in being with that species. All right, so here's just a picture showing the intermolecular forces between the water molecules. So water gets to have these intermolecular forces, the hydrogen bonds with each other, and it is something that it cannot have with the oil. So it effectively shoves the oil out of the way. So if we go way back here, the reason that oil is going back up to the top is as one water wants to link up with another, it shoves that oil up. It really kind of pushes it out of the way, and that's how we end up getting the separation again. So any questions about that? It's kind of a weird thing. I know it's sad. It's like water is bullying the oil, being like, no, you can't play with us. Go away. And eventually it goes up to the top. Very sad. All right. So let's see. So I think I want to lecture just a little bit longer, maybe about 20 more minutes. Do you guys want to take a 5-minute break or a 10-minute break? All right, so I see lots of 5s coming in, so let's go ahead and take a break. Let's come back at 7 o'clock, and at 7 o'clock we're going to start talking about solubility and saturation. All right, so any questions about anything that we talked about before break? All right, so next up is solubility and saturation. So there is only a certain amount of these solids that can go into a solution, and you know that if you've ever cooked, you tried to make some chocolate, some fudge, you're getting lots and lots of sugar in. There's only so much you can get, and then the sugar falls to the bottom. If you heat it up, you can usually get more in. But at any given temperature, there's only so much that goes in, and after that, so good question, Trevin. You do not have to memorize the solubility of NaCl. So if I wanted you to know a solubility, I would give you that number. There's only a certain amount of a solid that can go in, and that is considered its solubility. That is the maximum amount that can go into a certain volume of water. And NaCl has a solubility of 36 grams per milliliter, per 100 milliliters of water. So into 100 milliliters of water, you can get 36 grams of NaCl, and that is not something you need to memorize. But if I were to give that to you, I would want you to understand what is saturated, unsaturated, and supersaturated. So saturated means you have the perfect amount. You have the maximum amount in solution. So when you're in class or here online, I try to saturate your mind with chemistry, which is I try to give you the perfect amount. I don't want any corner of your brain to be like, oh, I wish she gave us more chemistry, right? So I don't want to leave you yearning for chemistry, but I also try not to super saturate you, which is you leave and there's like chemistry dripping out of your ears and you're like, I can't remember half of what she said. She went too fast. So saturation is the perfect amount. Unsaturated means you could still dissolve a little bit more. And again, supersaturated is when you've got way too much in solution, or really anything over the 36 grams in the case of NaCl in 100 milliliters of water. So the story I like to tell to kind of help you remember this, and those of you who hate my analogies, just cover your ears for a moment, is think about a big family dinner. And so you finished your meal and you're feeling pretty good. And let's say your grandma or your aunt or someone says, hey, would you like a slice of pie? And you go, no, I'm saturated. I've had enough. Thank you for offering. And they say, really? I mean, I made this just for you. And you're like, okay, well, I guess I could have a piece. And they're like, really? Only one piece? Because, I make a whole pie for you. And you're like, okay, I could have a couple pieces. And pretty soon you're feeling super saturated. And I think everybody knows what it feels like to be super saturated. You ate more than you should have. And not to be gross, but sometimes later that super saturation, that extra stuff kind of comes up. So that is exactly what would happen for a solution. So you can super saturate it, but it will eventually, the excess will come out because it never should have been there. Now, unsaturated is if you were finished your meal and someone offered you that piece of pie and you were like, oh yes, right on, I'm still hungry, give me 5 pieces of that pie. So unsaturated, you're still a little hungry. Saturated, you are perfect and you are holding strong, being like, I'll take the pie home with me. Supersaturated is when somebody has talked you into having more than you know you should. And so any questions on anything there? All right. So supersaturation or supersaturated solutions are actually pretty fun to play with. Somehow you get too much stuff into solution. So for a solid, you can heat it up And again, if you've ever cooked desserts where you had to get lots of sugar into solution, that heating it up gets the sugar in. So for our solids, we do find that by heating, we can get more in. For a gas, we find that by putting it under pressure, that's how we get it into solution. And that's what they do when they're bottling soft drinks. They put it in a very high pressure environment, and that pressure pushes the gas down into solution. It needs to come out of solution though. Eventually, it has to come out. It does not belong there. So how it can come out of solution, here's 3 images on the bottom, and it says it needs a rough surface. So one way of doing that is a seed crystal. So this is a tiny little crystal of your solid, or it could, in the case of a gas, it could just be a solid that's got a little rough edge to it, and you throw it into solution, and what happens? As soon as it enters the solution, the small particles attach to that seed, and here it has fallen down to the bottom, and now down here at the bottom you see the crystal starting to grow. So there are all these tiny little particles that need to come out of solution, but by themselves it's really hard. If they can find a place, call it eHarmony or whatever you want to, where they can meet other crystals, other little tiny crystals, then they can start to grow. And this is actually the same principle behind why if you cut yourself, we put a tissue on there. The tissue acts as a rough surface, and the platelets in your blood need that rough surface so that they can congregate and start clotting the blood. So the platelets are already there floating around, but if one platelet cannot find another one, it can't start the clotting process. Same thing here. We have tiny little particles of solids, or in the case of gas, very, very small bubbles of gas. They need to find each other. They need to get large enough so that now everything can start to grow from that center. So a seed crystal is a great way to do it. Another way is scratching the glass. So this is actually something that happens frequently in organic chemistry. So you will make your synthesis. You're going to make your product and you look in it and you go, hey, it looks like there's nothing there, but I know I followed all the steps. And you take your beaker to your teacher and you say, I followed all the steps, but I don't see anything. What your teacher is going to have you do is scratch the glass. You're going to take one of the glass stir rods and you're going to scratch right along the bottom there, and it's really going to be one little, and you'll actually hear it scratch. For some people that bothers their teeth, but you'll hear a little bit of a scratch, and then you'll let it sit, and pretty soon it will look something like this. All the solid will start to come out of solution. It needed that rough surface for all the small particles to get together. So any questions on anything so far here? So supersaturated solutions are actually really fun to play with. There are ways to force things to stay in solution. So for example, our soft drinks are actually supersaturated in soda, which probably doesn't come as a surprise, but they have chemical agents in there to prevent the solid from coming out of solution. So that agent that they put in there prevents a seed crystal or a scratched glass from causing the kind of precipitation or solid formation you've seen here. So I want to show you an example, and this is a YouTube video called Hot Ice, but it's not really ice. It is a supersaturated solution. When the solid comes out of solution, it's very exothermic, and you're going to see it does look like ice, so that's why they're calling it hot ice. right, so those are our supersaturated solutions. So you got too much stuff in solution and it does need to come out. So here's a graph of temperature and solubility. So generally the solubility of a solid will increase with increasing temperature. And it says generally because every once in a while you're going to see something like so, and this is a cerium sulfate, and it's very unusual in that it decreases, the solubility decreases as things heat up. But for most things, you see the solubility increase. NaCl only increases a little bit, but there's some that increase dramatically here. Oops. There we go. So any questions about anything here? Okay. And by the way, I'm showing you this graph just to demonstrate what we're talking about, that in general, solids increase their solubility with temperature. However, occasionally they decrease. I'm not going to make you actually take readings or do calculations from this graph. All right, so next up are the gases. So gases, the opposite actually happens. So what we find is when you heat up a carbonated drink, then it's actually less bubbly. We keep them cool for a reason. So there is a reason that when you're driving down the street, you don't see some store saying, hey, we've got the warmest soda and beer in town. That would not taste very good. And that is because all the carbon dioxide would leave. So in order to get the gas to stay in solution, we need it to be cool. The cooler it is, the more of that gas will dissolve. And that's why we like our carbonated drinks to be cool. We also have a situation with some of our lakes and natural bodies of water. So we often have manufacturing plants and chemical plants near water, and it's not so that we can dump our hazardous materials in there. We're not terrible people. But what we do often do is we bring the water that is from a natural source like a lake or a river, and we bring it around the equipment just to cool off the equipment so it never has contact with the chemicals. And the theory is, well, hey, we're not doing anything bad. We're just bringing in cool water and putting out warm water. Well, that actually is something that we call thermal pollution. So if you heat up a body of water, a lake, an ocean, a river, the oxygen and the gases that would normally be dissolved in there cannot dissolve as easily. So especially our problem is with oxygen. So fish and other aquatic life need that oxygen. As you raise the temperature, because you've let that water come around your manufacturing plant, cooling off your equipment, but heating up the water, now the oxygen cannot dissolve as well. So overall, you're going to have a lower concentration of oxygen. So for the aquatic life in there, for the ecosystem, that actually causes quite a bit of damage, and again called thermal pollution. And it's based on this idea that for all gases, this time no exception, that whenever you heat it up, the gases are less soluble. When you cool it down, the gases are more soluble. So any questions on anything here? So here it says if we increase the pressure of a gas, we can make it more soluble. Let me actually check something. I feel like we're missing something. Sorry, I feel like we're missing a slide here. Give me just 1 sec to check my notes. I'm hoping I didn't accidentally delete a slide. This slide got deleted somehow. Let's see. Let's see. Oops, sorry. Oh, no, there it is. Okay, there it is. Never mind. Sorry, I was worried that I had accidentally deleted a slide, but I see it in here. Okay, sorry about that. Okay. So here it says if we increase the pressure of a gas, we do make it more soluble. So what happens when we bottle these carbonated drinks is they are bottled under high pressure. So they are in a sealed container. It might be like a box. It might be some kind of a larger device, but somehow in here, there is very high pressure. And when I say high pressure, I mean extremely high, too high for humans often. So this could be 4 atm, 5 atm, very, very high. That pressure effectively pushes the gas down into solution. So long as you keep the lid closed, that pressure is still inside of there. In this case, the CO2 that you're seeing is nice and dissolved. But as soon as you open up your lid, now it starts to form gas and it tries to escape because here we have lower pressure. So at the lower pressure, the gas will try to escape, but at the higher pressure, here the gas will stay dissolved. So just to show you another example of that, this is my very poor artwork showing the ocean. There we go, now it looks like a beach. All right, so this is our ocean. And you've probably heard that there is more CO2 in the atmosphere now than there used to be. So we have an increase of CO2 in the atmosphere. And what we talk about here is we have an increase in the partial pressure of CO2. So we talked about partial pressures once upon a time with our gases. So here the overall air pressure is still about 1 atm, but we have a higher pressure of CO2, meaning more of the pressure of that 1 atm is due to the carbon dioxide. All right, so what's going on is for the pressure of the CO2, it is now pushing down on the ocean and the other bodies of water. As it pushes down, what's happening is more CO2 is dissolved. So the CO2 is getting pushed into the water by this increase in pressure the same way it was getting pushed into the soda. Oh, I think I see the problem. Hold on a sec. I got a cat on top of the computer. Mia, I love you, but you gotta move. Yes, you do. All right. Oh, I know. I think this was muffling the mic. Sorry about that. 15 pounds of fluff on top of the mic there. There we go. All right. Better now? All right. Is the mic sounding better now? Yes. Okay. Thank you. Thank you for letting me know that it was getting muffled. I didn't realize she had decided to sit on top of the mic. All right. All right, so the idea was the pressure from the CO2 is pushing more CO2 into the ocean, just like the pressure of CO2 inside of this can, and it is a partial pressure of CO2, is pushing the CO2 into the soda here. So that is true. So Andrew brought up a really good point. So he's saying that, but what if the ocean is getting warmer, then it won't be able to absorb as much CO2. That is true. So that is actually a force going the opposite way. So as it gets hotter, global warming, less CO2 could be absorbed. But what we're finding, even though we have hotter temperatures, which is creating less an effect where we'll have less CO2, the partial pressure of CO2 is actually a greater effect, pushing more in. And the problem actually with the CO2 going in is that it reacts with the water in a reaction you learned way back in chapter 4 to create carbonic acid. And this is what we know of as ocean acidification. So this is making the ocean more acidic. But Andrew is right. As the temperature goes up, less CO2 can be dissolved. But between the two effects, we find that this effect right here is greater, so we still are getting more CO2. So just to show you sort of an environmental application of what we're talking about here, that as the pressure of a gas increases, more is dissolved, more is getting pushed into solution. So any questions on that? Sorry for my poor artwork here. All right, so here is the picture that I was looking for. So we have one more application of this. So we had a super saturated lake, Lake Nyos in West Africa, and it was super saturated with dissolved CO2. So what happened, and what we didn't know at the time, is that there were underground volcanoes kicking out very small amounts of CO2, but they were doing it constantly over hundreds of years, and we did not know it was super saturated until something happened. Sorry, I think I have a cat fur in my mouth. So something happened, and nobody who was there actually lived, unfortunately. So August 22nd, 1986, something happened. We think it was a landslide, but the lake suddenly released all of its CO2. So if you remember back to the hot ice video where he touched, or the person touched the container, and suddenly all that solid came out, something similar happened in this lake. Something went in. We think it was a landslide that had lots of rocks, that had very rough surfaces, that allowed that CO2 to all of a sudden come out, but it, boom, released all its CO2, or I should say all the excess CO2, and because CO2 is more dense than oxygen, it blanketed the land with carbon dioxide. All the oxygen was pushed above, and unfortunately all the people, all the animals in the area suffocated because there was no longer any O2. It all went to a higher level because it was less dense than the carbon dioxide. So nowadays we go around the world and we look for lakes like this, and if you go on Wikipedia you can find pictures of this lake, and it now has what looks like a little fountain in the middle, and it's actually a pump that is slowly pumping out the CO2. So it comes out a little at a time, so nothing like this would ever happen. And like I mentioned, we go around the world looking for lakes like this where something like this might happen to make sure this never happens again. But this was a super saturated solution. So any questions on anything here? So carbonated beverages, they're also super saturated with CO2. So carbonation means it is super saturated in CO2 by definition. So you can use a rough surface to catalyze the release of CO2 from a carbonated beverage. You could throw in some dirt or some salt, and I know it sounds horrible, you take your favorite beverage and throw in dirt or salt, but it is very interesting what's going to happen. It will cause crazy bubbling. So what I used to do as a demo is I took some club soda, because you can really see it well in the club soda because it's a colorless solution. Open it up and throw in especially some salt, because salt has very rough edges, and it will suddenly bubble like crazy. And that's a great fun experiment to do at home, especially if you have little kids or if you're a little kid at heart. And you will see all the excess carbon dioxide just bubbling on out. So we're going to take a look at a video of the famous Mentos and Diet Coke experiment. If you haven't seen it before, it is amazing. If you haven't done it before, this is what you should do while you are staying at home on quarantine, the Mentos and Diet Coke experiment. So let's take a look at it and then we'll talk about it.
Well, here we are at NAYC, and Drew, our trusty intern, is making sure that people can understand the Mentos and Diet Coke. When you pull, the Mentos will fall, all the carbon dioxide runs to the pits on the Mentos, and we get this beautiful reaction that takes place. It's tiny, you can barely see it. Come here, help me out. His mom and dad think that he's on some sort of learning adventure. He's not, he's just standing in this, all right? So watch this, go ahead and give a little pull. It'll just pull, nice, Drew.
idea of the Mentos and Diet Coke experiment is that Mentos, if you've never had them, they have tiny little pits on them. And these little pits are very good for formation of larger bubbles. So what's happening, similar to what we talked about with our solids, is tiny little bubbles that are too small to come up to the surface on their own will get into one of these pits. And it becomes like an E-harmony down here, all these tiny little bubbles that are getting together in this pit, and then they merge and become a larger bubble, and now they're more buoyant, and now they can start going up. But when they were just those tiny little bubbles, they were too small to rise to the surface. But once they got together, they were big enough to come out of the solution. So that's how the Mentos work so well. Back in the day when I taught chemistry, we did some experiments to see, which soft drink really did the best job, and we find that Diet Coke does the best job. It's because of that, we think there might be a slight chemical reaction going on in addition to just the Mentos providing a nice pitting area. But these Mentos do work for any carbonated drink. So if you had your club soda with a large enough opening, you could throw these into your club soda and you'd get a similar reaction. All right, so questions on anything here? All right, so here's a summary of what we've talked about. So on the left are our solids and on the right are the gases. So here are solids. So at a higher temp, most of them are going to be more soluble. So not all of them, but most of them. At a higher pressure, we don't see much change for our solids because solids aren't very affected by pressures. And if you have a supersaturated solution, some kind of a rough surface like a seed crystal will help it crystallize. On the other hand, our gases, at higher temp, they're actually less soluble. So if you are looking for a good carbonated drink, you don't want it hot, you want it cold so that carbonation stays in there. At a higher pressure, they're more soluble. So we pressurize our cans of soda to keep those gases inside. And then the crystal or rough surface will help our supersaturated solution. It will help it release all the stuff that should not be in there, where we got too much stuff in solution. So any questions on anything here? Okay, so one last thing is I want to try this one as practice. So it says a solution is saturated in both nitrogen gas and potassium chloride. So by saturated, I mean it's got everything it can have in there. It is stuffed, no pie, I've had enough. So it's saturated in nitrogen gas and potassium chloride, and this is a solid. And it's at 75 degrees Celsius currently. So then what we're going to do is we're going to cool down the solution to room temperature, and I want you to think about which of the following would occur. Some nitrogen bubbles out of solution, some potassium chloride precipitates out of solution, that means it forms a solid, both A and B, or nothing happens. So let's take a minute or two, give this a shot. Those of you who are brave, feel free to put what you think into the chat box, and we'll talk about it together. All right, so Andrew is suggesting a B. How about the rest of you? What do y'all think? All right, so it looks like Jervin and Juan agree. Let's take another minute or two and to kind of mull it over, and then we'll go over it together. All right, I went ahead and launched the poll, so go ahead and click in if you'd like some more time or are you ready to go over it. So it looks like a couple of people want some more time, so let's go ahead and take another minute or so. All right, so let's go ahead and give this a shot. So before we solve the problem, let's talk about what's going on when the solution is cooled. So I am going to decrease the temperature, and I want to think about what's going to happen to a solid and what's going to happen to a gas. All right, so when we decrease the temperature, what happens to the solubility of a solid? Is it more soluble or less soluble usually? So as we make it colder, is it more soluble? Okay, there we go. Less soluble for the gas, excellent. So as temperature goes down, the solid should get less soluble. And I saw in there that the original comments were for the gas, so it is true. The gases get more soluble. So just to kind of finish out this table, just so we have it, if we increase the temperature, this is when the solids get more soluble. And the gases get less soluble. All right. So any questions on what I've written here so far, that when the temperature goes down, solids will become less soluble and gases will become more soluble? And when the temperature goes up, solids become more soluble and gases become less soluble? Just so it makes a little more sense, let me go ahead and put this into a chart. There we go. Okay, so now let's go ahead back up. So it says some nitrogen bubbles out of solution. If we dropped our temperature, the gas would be more soluble. So it doesn't make sense for some to come out of solution. So I'm going to say that A does not occur. Next up, some potassium chloride precipitates out of solution. Well, if we drop the temperature and it's now less soluble, that would make sense for some solid to start coming out of solution. C says they both happen, and D says neither one of them happen. So it does look like our popular answer of B is correct. So any questions on what we've talked about here with when we drop the temperature, solids becoming less soluble and gases becoming more soluble? Or when we increase the temperature, solids becoming more soluble and the gases becoming less soluble? Any questions on anything that we've talked about tonight? All right, so come Wednesday, it will be our very last lecture. We will finish talking about solutions. For the rest of tonight till 10 o'clock, I am here. If you guys have any questions for me on lecture or lab, I've heard there's a few questions on the graphs, but I am here for you guys. So do you have any questions on anything?